This week we're going to talk about static electricity. And as the name implies, it is electrical charge that is not moving. Static electricity is the buildup of electrical charge on the surface of an object, but by its very nature it does not move. Now, when you talk about electrical current, the term current gives you the idea that the charge is moving. And so static electricity is electrical charge that's present but generally not moving. Electromagnetic forces, which we will begin to talk about with this chapter, is one of the four fundamental forces in nature. The four fundamental forces in nature include static electricity, moving electricity, and magnetism. All of these are associated with electromagnetic force. And then also gravity is one of those four fundamental forces. Now let's take a look for a second at the idea of conservation of charge. First of all, an electrical charge is a physical property of an object that results in either attraction or repulsion from another object. It is due to an imbalance of either positively charged protons or negatively charged electrons, which results in a overall positive or negative charge. So if we look, for example, at this first diagram, we see that the charge occurs because we rub the silk cloth on a glass rod, and what ends up happening is electrons are transferred from the rod to the cloth. Thus the cloth becomes negatively charged and the rod becomes positively charged. And since there are opposites, the rod is actually attracted to the silk. In this second situation, you have a second rod that's also been rubbed. Now both of these now are positively charged, and because both of them are positively charged, one will repel the other. Similarly, if you have two claws, both of which are negatively charged, they will also repel each other. And this leads to one of the laws of charges, which is that opposite charges attract and like charges repel. Now, charges are due to transfers of either electrons, which are the negatively charged particles around the nucleus, or protons, which are the positively charged particles in the nucleus of the atom. Now generally it's a transfer of electrons that occurs as opposed to a transfer of protons, because the electrons are more vulnerable to physical trauma and to being transferred than the protons are. This diagram shows the planetary model for the atom. In the planetary model, electrons orbit the nucleus like moons around a planet, and the protons are in the middle, and they are heavier and more easily retained compared to the electrons which surround the outside. Now this picture right here is something called a Van de Graaff generator. A Van de Graaff generator is a machine that produces excess charge. And in this case, what we have is when a person touches a Van de Graaff generator, they actually develop extra positive charges in their body, and because of the extra charges, their hair stands up. And what we're looking at here is a single hair that has multiple positive charges, less negative charges, and that's why it stands up and it sort of separates from each other. Now, the charge that we see is a result of microscopic particles called quarks. This is a conception of a quark, or a model of a quark. The quark, it takes 3 quarks to make a particle, and when 3 quarks add up to a positive, then you have a proton, and 3 quarks add up to a negative, you have an electron. Now here we have something called conservation of charge. When you start out with 2 objects, you have to end up with the charges being conserved as it moves along in this direction. So you start out, you have 2 positive charges and 2 negative charges. The net here is negative. Similarly with the cloth. Now, You take the amber and you rub it against the cloth, and there's a transfer. There's a transfer of negatives to the amber and positives to the cloth, but you end up with the same number of charges together. You have 5 positives and 5 negatives, and here you're going to have 5 positives and 5 negatives. This is the law of conservation of charge. That is, the total charge is constant in any particular process. So when you start out, they're neutral. They have no net charge because the balance between the two charges has occurred. However, after the rubbing occurs, negative charges are transferred from the cloth to the amber in this case, and leaves it with a positive charge on the cloth and a negative charge on the amber. And yet overall, as I said before, you end up with the same number of charges total, and if it's a net negative 2 over here, it has to be a net positive 2 over here. Now when you talk about insulators and conductors, a conductor is any material that will allow electrons to move freely through its atoms. An insulator is a material that does not allow this to occur. Now you may or may not remember that when we discussed chemistry and bonding, that conductors are generally things like metals because of the free electron theory. Insulators are generally things that are bound covalently, that hold on to their electrons and don't allow electrons to move freely. And so you have, in this case, you have a metal inside a rubber coating, the rubber coating acting as an insulator, and the metal acting as the conductor. So this adapter has metal wires, which are conductors, and it's surrounded by plastic or rubber externally, which acts as insulators and separates the conductors from each other. And this is something called a galvanometer, which is a machine or a device that can measure whether charge is present or not. And what happens is that you see that charge is present by taking advantage of the electrostatic repulsion that occurs when like charges come close to each other. In the situation A, you start out with a positive rod that attracts negative electrons to this part of this situation. This leaves only positives in these foil leaves, and because positives repel, these leaves separate. And so you know that this has to be charged because it resulted in this reaction. Now, when they touch, electrons are transferred. And because they're transferred, you see that there's some loss of positive here, and some of the negatives come back down here, and the leaves are not as far apart. Then when you remove this, you still have an imbalance, but these become evenly distributed throughout, and you're left with a modestly separated leaves. Now, induction is a process where charge is created in a nearby object. So you start out in situation A here. You have 2 neutral metal spheres that are in contact with each other, but they're insulated from the rest of the world. So you start in A in a situation like this. By the way, the term polarization means the separation of charges. In B, you bring a positively charged device or substance or whatever you want to call this, rod, and it attracts negative electrons here. And what results is over here, because negatives are attracted this way, the positives go away from or to the right, and you end up with polarization, separation between the negatives here and the positives here. Now with the rod still in place, you then separate these two so that charges cannot move, and you make it permanent so that they can't move back if you remove the rod, they can't move back where they were before. And this polarization makes the polarization permanent. And then once the rod is removed, then the negatives are attracted by the positives here, but they're not touching. So, and you end up with a situation of induction. You can charge by induction with a ground. You start out again with a single, instead of two spheres, you start out with a single sphere. You move the rod close. The negatives are attracted, the positives move away. With the rod still in place, you then attach a ground, which allows electrons to be attracted from the Earth's ample supply of electrons. And so they come up and they neutralize some of the positives here. And then you unhook the ground and you've removed the positives because they were attracted by the negatives of the ground. And you break the ground connection, and then once you move the rod away, your resulting sphere is negatively charged. When both positive and negative charge they attracted by a neutral object, when you put positives and negatives close to a neutral, because they're close, they polarize the molecules in that substance. So here, a positive rod is brought near to a neutral insulator, and this polarizes the molecules within the insulator. Now, it's an insulator, so there's not free transfer of electrons. So instead of all the negatives being over here and all the positives being over here, what you end up with is each molecule orients itself so that its negative end is toward the positive and the positive end is toward away from the positive. Conversely, if you move a negative object close, you end up orienting exactly the opposite way. And then, as we showed before, you put a conductor here with a negative object, and the positive proton goes in this direction, and the negative moves away. Now, let's talk for a second about Coulomb's law, and then we will do a couple problems related to Coulomb's law. Coulomb's law is a means of calculating the force that is generated by this attraction, well, in this case, repulsion or attraction. And the two things that control the force are the level of charge of each particle and the distance between the two. So an electrostatic force is the energy and direction of force due to the charged bodies being brought into some degree of closeness with each other. The magnitude of that force can be calculated using remember, the like charges repel and unlike charges attract, and the force is the same. It's equal to a constant times the absolute value of these two charges, the level of these two charges expressed in coulombs, and that whole quantity divided by the distance between the two squared. In this case, K is equal to 8.988 times 10 to the 9th Newton meter squared per coulomb squared. And this is a formula that you need to remember. Now let's move on and do a couple problems. The first of these problems, how strong is the attractive force between a glass rod with a charge of 0.7 microcuries and a silk cloth with a charge of minus 0.6 microcuries if they're 12 centimeters apart, and you pretend that they're point charges so you don't have to worry in terms of the distance. You don't have to worry about, is the whole charge in the same distance from each other. So in order to do this, we start out with the formula that I just showed you, which is F is equal to K Q1 Q2 divided by R squared. Now in this case, K is 8.988 times 10 to the 9th times Q1 is 0.6 or 6 times 10 to the minus 7th coulombs, 0.6 microcoulombs, and the other one is 7 microcoulombs times 10 to the minus 7, and this is all, and this is all divided by 0.12 meters squared. Remember, this is Newton meters squared per coulomb squared. And so if we do the math here, we end up getting 0.262 newtons. Now because these are opposite charges, they would be attracting. So the direction would be, one would be toward each other. Now the second problem says a test charge of plus 2 microcoulombs is placed halfway between a plus 6 charge and a plus 4 charge. Now these are all positive, so they're all going to be repelling each other. And it's separated by 10 centimeters. So the plus 6 and the plus 4 are separated by 10 centimeters, and we put this 2 right in between. So what is the magnitude of the force of the test charge on the test charge? So what this is you have two charges. One is excuse me, plus 6 micro, the other is plus 4. And in the middle, in between these two, you put another charge of plus 2. All these are microcoulombs. Now you know that the repulsive force here is going to be less than the repulsive force here. So ultimately the direction is going to be toward the 4. Okay? And so we use the same formula and we calculate the same calculation for the 4. So when we do it with the 6, we put the 6 in there. We get, when we put the 6 in there, we get 0.43104 newtons. And when we put the 4 in there, we get 0.28736 newtons. So in one, we've got 2 microcoulombs and 4 microcoulombs. These two are the same. I'll show you one of the two calculations. This would be 8.988 times 10 to the 9th times 6 times 10 to the minus 6 times 2 times 10 to the minus 6. And it's going to be divided by 0.05 squared, okay? And that's going to end up giving you this number. The second calculation, you just change this to 4 and you get this number, and then you just subtract the 2. And when you subtract the 2, you get 0.144 newtons, and the direction here is going to be away from the 6 microcoulomb charge.